First of all, I'd like to reset your mentality from the mentality of student to the mentality of lecturer or teacher. So, actually, what I'm trying to do through this coursework is to develop some methodology for teaching, so you can develop same mentality as I'd like to help you for you to develop. Also, you can develop your own methodology for lecture or teaching. That's the point I'd like to share with you. Also, I'd like to remind you what we have studied from last semester by reading chapter content together. Last semester, what is unique in crystallography is its unique vocabulary, first of all. Vocabulary, even if you use the same alphabet, ABC, alpha, beta, gamma, meanings are not the same. Also, if you use 1, 2, 3, 4, 6, the meaning numbers are not the same. It's not about arithmetic computation, it's about symmetry. So, from chapter 1 down to 6, particularly 5 and 6, we studied core knowledge about crystallography. You can regard those two, 5 and 6, fundamentals of crystallography, geometry and diffraction. Geometry from mathematical point of view and diffraction from the physical point of view. So crystallography is a multidiscipline between mathematics and physics. Mathematics for ideal situation, physics for real situation. We are linking some ideality and reality. That's what we have done from chapter 1 down to 6. Then we are studying other aspect of crystallography, practical aspect. These are not very related to former one. So we have kind of jump, although we are using same terminology. But our focus will not be the same. Previously, it's about learning new vocabulary. But this semester, we will not learn anything new from the point of symbols. We will use the same symbol as we have used before, but we will focus more on scientific aspect. So treatment of data and building model and building kind of theory or simply model in this case. So today, in addition to previous one, I'll talk about determining your structure part and reconstruction, phasing, etc. down to model building environment. But before starting this, I'd like to talk about this sidebar in your textbook. But regard this textbook as a kind of a picture book. Even last time and this time, I will go through topics with pictures. What pictures are you looking at? What you are looking at? We have two kinds of animals. Which is which?
Duck and cat.
Yes, dog and cat. So, if you read this sidebar and box, actually this is taken from the textbook, this textbook. Not only this book, but also many crystallographic illustration, also tutorials are using this kind of picture. Simply here is our old friend Fourier dog and transform, etc. But do you know the Alice the Wonderland? What is the book? Alice Wonderland.
Oh, Alice the Wonderland.
Yeah.
Alice in the Wonderland.
Yes, Alice in the Wonderland. Yeah, you are correct. Not Alice the Wonderland. Alice is not the Wonderland. Alice was in the Wonderland. Yes. So Alice in the Wonderland. Alice in the Wonderland was written by famous mathematician. Also, he was a novelist. But it's fun to read such a book, isn't it? Likewise, crystallography can be a fun if you know both aspects, kind of pictogram like this, and meaning behind that. Unless you know the meaning of picture itself can be meaningless. But if you know the meaning of picture, it can be fun to play with. If you know some logic behind Alice in the Wonderland or philosophy behind Alice in the Wonderland, the book may not be children's book. It can be a book for adult, even mathematician, in terms of its symbol and its analogy, etc. Likewise, crystallography can be very hard science for you because it not only involves biology from the perspective of protein part, but also physics from diffraction part, also mathematics from because of its computation. But computation can be explained in terms of picture like this. Here, Fourier transform was explained in terms of pairs of picture. What is in left column? What's in any left, right, and left? Here we have two pairs of figures. One is dog, the other is something. What's written there?
Fourier transform.
Of what? Duck, so-called Fourier duck. Left side, simply real space duck. Right side, it's Fourier pair, so-called Fourier duck. Fourier duck, you cannot recognize any shape of duck, but still, mathematically and computationally, it is directly related to original one. Likewise, on top of right column, at left side we have cat. What is in the other side? Yes, Fourier cat. Fourier transformed the image of left side cat. Okay, there are pairs in each respect. Then we have some explanation about transformation and interpretation, etc. So my suggestion for you is like this. Don't take crystallography too hard. Crystallography can be a picture book for adults, not for children. It may not be for children because it should involve your own thinking at higher level, like Masters of Science or Doctor of Philosophy. But still, it's so simple in terms of presentation, like this. So once you develop some skill for thinking or skill for transforming ability in your logic, then all things can be very simplified. Beauty of crystallography and beauty of thinking in crystallography should be like that. Simplicity once you master complexity. I cannot say mastering crystallography is easy, but once you capture main idea, I'm not asking you to master all the details of crystallography, but as a mature and adult learner, especially for Masters of Science and Doctoral Philosophy, with your own intelligence, within your own capability, I'm not talking about physical capability, I'm talking about intellectual capability. You should capture main idea like this, and you should be able to follow the discussion or pictures presented in a book like this. Then you will be very competent as a scientist. Even you can have discussion with engineers. Normally, engineers and scientists may not have the same set of mentality, but Once you master core skill set for crystallography, or the way you should think as a crystallographer, then you're very good at interfacing many experts like science and engineers alike. So if you have time and think about the meaning of two pairs in sidebar like this, and don't take this as a homework, but when you are bored with your ongoing research, open this book as a picture book. Go to this page and try to understand what is the meaning behind pictures. Then this textbook will be more like Alice in the Wonderland. So that is my wishful thinking, but it's up to you. And again, chapter 9, detailed contents. Anyway, former part, we should establish vocabulary. Now we already have such a vocabulary, basic vocabulary, FHKL, density at XYZ. Also for XYZ, we have basis vector ABC. For HKL, we have A star, B star, C star. More than that, we do not need any mathematics. Simply, both functions are related with Fourier transform. Now we are jumping into Fourier transform again with the title like this, The Phase Problem. So today I will focus on the problem in crystallography, the problem in protein crystallography for you. Also, to learn about phase problem, we need to know how electron density can be reconstructed from structure factor. Here we have section 1, reconstruction of electron density, and section 3, phase problem and phases in electron reconstruction. More than that, we have some extra sections like this, effects of incomplete data in electron density reconstruction. Also, Peters function and Peters maps, which are similar to electron density function and electron density map. If you have questions, I'll provide more explanations, but by now, let's talk about electron density as a function. Starting with here. We talked about this picture. What's in right side? Electron density in quanta form, three-dimensional quanta form. Also, what's in left side?
Diffraction data.
Yes, simply diffraction data in terms of HKL indices as coordinate and structure factor magnitude FHKL at each coordinate in reciprocal space, coupled with phase angle at those indices. Okay? Then why we are saying that right side or electron density, we need to distinguish its function and its presentation. Here, what we are actually looking at is not the function itself. It's a three-dimensional representation of such a function. So time to time, even the author of this textbook were confused about such a distinction. But if you are confused about such a distinction, we cannot develop some understanding. So I'm trying to ask you to pay attention here. Here, chapter 9, reconstruction of electron density. Is that representation or function? What we are talking about here? When we are talking about reconstruction, what we are talking about in reality is that contour diagram or function or data. What we are talking about? Electron density.
This is
Reconstruction.
just representation.
Hmm?
This is contour diagram, and this is just representation of the data.
That's the point that I'd like to correct. In reality, in terms of information, this is degenerated. With this two-dimensional picture, we cannot reconstruct this. Also, as I mentioned last time, we should have more data around possible HKL. This is just very little part of whole data. Don't be deceived by textbook explanation. As a master of science, also as a doctor of philosophy, you should be able to reconstruct real meaning behind this kind of representation of reality. Here, we have only part of, very small part of data. Here, we have just figure. These are not the data. Okay? But to demonstrate what the author is trying to explain, we just have some representation of HKL data, and we have some representation of such an electron density function. But this figure itself is not a function. This part of data are not whole data. Okay? You need to distinguish those concepts, reality and representation. These are representation of real data. This side, representation of real function. Real function on space, XYZ space, or ABC vector space. Okay? Otherwise, you will be confused about its representation and reality. We need to distinguish those two. Reality, representations are not the same one. Reality, to capture or reconstruct reality out of this representation, you need to develop kind of scientific imagination. Okay? Let's count how many data here. 1, 2, 3, 4, 5, 6, 7 point only. 7 point, at 7 point of HKL coordinate, we have F, magnitude, and phase angle. That's all. Very limited. How many data did you collect out of your synchrotron trip?
It's more 200.
Hmm?
About 200.
Even out of single frame, usually 1,000 spots. If you collect more than 100 times 1,000, more than 10,000. Usually we are dealing with 100,000. Point like this. Very small part. Also, out of two-dimensional figure like this, we cannot construct electron density. But if we have electron density function, out of such a function, we can calculate or we can draw like this using computer software. So representation and reality are not the same one. But using this kind of representation or small set, subset like this, we can develop some idea. But you should not limit like children. Children book, Alice in the Wonderland, can be read by adult learner or adult reader. It can provide more meaning than before. Likewise, most crystal textbooks contain figure like this. But out of this figure, as an adult learner, you should exercise your part, your role, to reconstruct real meaning behind the data and behind model or function. So, through such intellectual exercises, reading book like this can be intellectual challenge. It cannot be boring. Even if you are not doing research in crystallography, crystallography can be a kind of intellectual exercise for, this is my wishful thinking. This is not general claim, but my wishful thinking is, as a introductory coursework for any kind of Master of Science and Doctor of Philosophy, crystallography can be very good training for multidisciplinary scientists, engineers. That is my point. Anyway, here, having those concepts again, chapter. If you go through reading the whole chapters or whole sections, you may be lost with such a details. But by looking at chapter content like this, you may capture some keywords. Keywords like this: electron density. Electron density is function, like Patterson's function. First of all, what is Patterson by your common sense?
Some scientist.
Yes, Patterson is kind of family name. Here, Patterson was an American crystallographer who used his the named function according to his own family name, Patterson function, to determine or to solve phase problem. So, Patterson function in crystallography is related to electron density function in crystallography. I will not explain Patterson's function today, but as a scientist, I'm asking you to develop some analogy between electron density and Patterson. If you add function del, electron density function, then we have Patterson function. If you may not remember, but last time, before data collection and after crystal geometry, just at diffraction basics, I was talking about symmetry. Symmetry in real space and symmetry in reciprocal space. At that time, I was talking about point group symmetry and space group symmetry and Patterson symmetry. Somewhere between there, we have Patterson symmetry of Patterson function. So we have real space symmetry in electron density function. Also, we have reciprocal space symmetry in diffraction space or reciprocal space spots. Anyway, Patterson function, like Patterson function, what we should have here is electron density function. But for our own sake, in terms of economy of language, rarely we are using the function here at electron density. Density is a function, so we are not saying electron density function. We are just saying electron density. But Patterson's function, to be parallel with the terminology Patterson's function, we should say electron density function. Also, transformation in mathematics is the way to convert some function in some space into the other function in the other space. So electron density function can be converted to structure vector function in reciprocal space. But likewise, we are not saying structure vector function for the economy of language. We are just saying structure vector. But as a role in computation, electron density is a function in real space. Also, structure vector is a function in reciprocal space. Peterson function is a function in real space or Peterson space. Real space and Peterson space are related. Okay. So here are Fourier transformation, computing Fourier integrals and summations. Integrals and summations, if you read the textbook, it's like integral for continuous function, summation for discrete function. You know the word continuous and discrete. 왜 전화거든? Excuse me. Sorry. And here, here. Three-dimensional electron density map. Here, Peterson map. What I'm trying to share with you is symmetry in vocabulary. We learned symmetry in space and symmetry in diffraction space or reciprocal space or structure vector function. Now I'm trying to share symmetry in vocabulary, electron density map, and Peterson function and Peterson map. Although you may not learn something about in Peterson function and Peterson map by this kind of analogy, you may be able to predict what the function is in Peterson space, Peterson function and Peterson map. So what is electron density map and what is electron density? What's the difference between the word electron density and electron density map? In particular, we have electron density map. What the author is talking about using the word map.
Map is the presentation of electron density.
Correct. Bingo. Now we have correct word for presentation of electron density, like two-dimensional map or physical map. But unlike our world map or city map, this map is a capture of three-dimensional object. City map and world map, basically, although the object itself is three-dimensional, we are dealing with two-dimensional space. Only the height can be presented with its contour. But object itself is three-dimensional. Then we have trouble, unlike world map or city map. What trouble do we have in terms of difficulty to present the map object?
You can only present in 2 dimensions.
Also, this is the quantum problem. And to save time, I'll show this again. Here, how many contour levels do we have? This is a question you should answer. We have talked about electron density. Now we are talking about electron density map as a representation of electron density function. But my question is like this. How many contour levels do we have in this particular figure or picture?
Levels?
World map or city map. In world map, we have green one and yellow one, or anyway, depending on height, we have different color. Even not only color, we have some contouring level near to Everest, near to your own home country. We have highest position on the world. Okay. Likewise, near to our place, we have some hill there. Near to hill or near to mountain, we have many levels, several levels. But flat space, plain, we do not have any level, contouring. So level present, we can say 100-meter level or kilometer level. So depending on scale and purpose, we can use different scaling or different leveling.
3.
Number 1, 1. Number 2, 2. Number 3, 3. Number 4 is nothing else, something else. This very simple question, you should answer this kind of question with your confidence. Firstly, what is the definition of level? L-E-V-E-L. Also, what is the purpose of contouring? Same level.
The more darker is more near to us, and the lighter one is far to us.
That can be very misleading observation, but still correct. In terms of three-dimensional feeling, this kind of contouring can be done with darker part and brighter part. So it gives us kind of three-dimensional sensation. But if I give you answer, here we have only one level, no more. One level. Huh? You should think for yourself. Why or how? But I will not answer how, but I will answer why. Why only one level is drawn, unlike city map or world map. City map, we may use many levels to present some concept of height. Otherwise, low, high, very monotony. But even in city like Daejeon, we have variety of heights. Near to Shinseongdong, flat, but near to here we have observatory, city observatory, little bit higher than surrounding. Also, surrounding Daejeon city, we have many higher mountains like Gyeryong Mountain, etc. To notify its relative height, we need to several contour level. But here, we have only one. I will not explain how one, but I'll explain why one. If you are trying to present more than one, figures will become too complex to capture its meaning. So, to be simple, because it's not two-dimensional presentation, it's already three-dimensional presentation. So, by limiting one contour level only, we are presenting some concept of surface. This will be exercise. How one level is drawn, but it has something with EQ. Anyway, for contouring in city map or physical map, what we have is same height level. Likewise, these the surface here are representing such a same height or same functional value. Think about that for yourself as your own intellectual exercise. Anyway, crystallography is kind of picture book. Most time, as I reflected what I tried to teach you, I recognize that I have shown figures or pictures always. Then by looking at such a pictures like this, I try to share some concept like this. So unlike novels, unlike some textbook from human science or social science, our textbook contain lots of figures. So you can think in terms of figures, not in terms of text alone. But time to time, you can read text and you can reconstruct the true meaning of representation. Okay? Then reading this book may not be boring again. Kind of intellectual challenge all the time. Even with Sanguk and Muhammad, I notified many mistakes. Time to time, we found simple mistake in typo, also some mistakes in equation, also conceptual mistake in explanation. I'll talk about something like that today again. But don't take this book as a perfect one or error-prone one. Still, not only in typographic errors, but also conceptual ones are contained here. You need to correct them with your own intelligence. But once you develop this kind of mentality and this kind of ability, you will be really competent as a scientist or simply as a professional. That's the point I'd like to help you. Here, real space and reciprocal space. The word convolution. I'll not explain the word convolution, but take this as an exercise in vocabulary. Here, real lattice. What lattice do we have here as a pair, Fourier transform pair? And this is quiz, quick quiz. Real lattice. Which lattice? Yes, reciprocal lattice. Yes, that's correct. When I'm asking you as a quiz, I'm expecting prompt answer, even if it could be wrong. Wrong answer can be better for me to explain something. So, real lattice, reciprocal lattice. We learned this kind of concept from last semester. Here, protein structure. Here we have something, but it's a little bit tricky. To be helpful for you, I should say electron density, but it was not drawn like electron density map. It was drawn like protein structure. So you have the word structure here, and what's here?
Structure factor.
Oh, bingo! Electron density function, structure factor function, but that's for your understanding. So to be brief, electron density as a function, structure factor as a function, but structure factor, that could be simpler. Structure in real space, structure factor in reciprocal space. Okay. But here a little bit tricky. What do we have? Anyway, I'm asking you as a quick answer. Forget about this symbol. Lattice, real lattice, protein structure. If you put protein structure at every lattice, what will we have as a result? Unicell here. But this is more than unicell. Oh, bingo! Sabah gave us correct answer. Protein crystal. Crystal made of protein inside. So, anyway, simple answer is crystal. Lattice. Lattice is not crystal. Lattice is kind of imaginary partitioning of three-dimensional space using vector ABC. If you have such a partitioning in space, we can imagine we are putting protein at each lattice. Then, actually, this is the process we are growing protein crystal. Actually, in the solution, we are trying to bring a protein out of solution into the lattice. But we do not have cage like this. Do you have this kind of cage? You didn't have this kind of cage. Once proteins are aggregated or assembled, then we can imagine this kind of cage still, but we cannot have such a cage as atoms, but just as a mathematical way to think assembly of proteins with crystal condition. Okay, so then anyway, crystal. Then what is this? Fourier transform of crystal. Before jumping into that, when we start course of today, we talked about duck and Fourier duck, and cat and Fourier cat. Okay, likewise, we have something else, crystal and
Furious transform of proteins, crystal diffraction data.
both are correct. But to be precise, a little bit tricky, but what's the difference between this one and this one? This one, this one, this one.
This one is 2D and this one is 3D.
Ah, very nice, misleading conclusion. Very nice, but misleading. So we should have kind of full proof. We should prevent from that direction. Here, although it was drawn in 2-dimension, this is also drawn in 2-dimension, but it gives us meaning in 3-dimension. Likewise, 3-dimension. Actually, protein has no meaning in 2-dimension. Photo like this. Actually, it has meaning only in 3-dimension. Likewise, why should we have 2D with 3D? If this is 3D, equivalent should be 3D. 3D, 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 or should have meaning only in same kind of dimension, although they are not in the same space. Okay? So, if you look at this and this, I'm just giving correct answer. This one, continuous function. This one, discrete function over integral HKL. Okay. I'm sorry to give correct answer, but to save time, I gave you. Anyway, if you look at this, lattice, lattice, continuous function of electron density, continuous function of, we should be a little bit careful here, continuous function of electron density, continuous function of Fourier transform of electron density. This is the exercise. Duck, Fourier duck. Cat, Fourier cat. So, reciprocal lattice is Fourier pair of real lattice. This one is Fourier pair of protein structure. So we are tempted to say this is also structure vector. Structure vector, or Fourier transform of structure is structure vector. But this is problem. We are not saying this is structure vector, but I'd like to say structure vector. Structure vector actually this side. Structure vector as a function FHKL. HKL is kind of discrete or integral coordinate. But here, continuous one. So structure vector by definition is for this side. So what is structure vector in terms of the word protein crystal? Who will answer? What is the definition of structure vector in terms of crystal? This should be simpler. Dog, Fourier dog. Cat, Fourier cat. Crystal, Fourier crystal. Full word, in terms of full wording, Fourier crystal is Fourier transform of crystal structure. Okay. Then this is structure vector by definition. So structure vector, discrete function, but this one is continuous one. If you look at point like this, the author was trying to give meaning like this. Here at the center, a bigger one, and so we have some matching over function value here and function value there. Actually, like this, we are putting protein structure here in terms of ABC. Likewise, we should put Fourier transform protein structure here. Fourier transform of protein structure here. So if you look at this and this, we are looking at same lattice. What's the difference between this figure and this figure?
In this first figure, we have not put this one continuous Fourier transform of protein molecule, but in this third figure, we have put the Fourier transform of protein molecule in the crystal lattice.
That can be correct one, but to be simple, here everything is same. 1 over A, 1 over A same, A star same, 1 0 0, 1 0 is same, 1 over B same. But here, if you look at origins are not the same. What's the difference? Also, if you look at this point, not same. So the author tried to add something at each vertices, okay? Each point. That is the function value taken from where?
Crystal.
Not from here, but from here. So this is not drawn properly, overlapped here, like this photo of protein structure is not very good scale. It's not in good scale to be fitted here. But anyway, this one was fitted there. But this one is not fitting in unicell of this. Actually, unicell has only meaning in real lattice. It's not for here, but over HKL in the same scale. I'll not explain this again, but difference between here is like this. This is symbol of convolution. In terms of your operation in thinking, symbol of convolution means you should put each your motive like this in each lattice. That is convolution. Repeating motive over whole periodicity along ABC. Then you will have copy like this. Like PCL, this is kind of amplification. Amplification of single motive over whole places captured in each unit cell. But here, this is not like that. This is simple multiplication. Result of Fourier convolution in crystallography is like this. Convolution of real lattice and protein structure is equal to protein structure, protein crystal. Then Fourier transform of protein crystal, by definition, structure vector. Structure vector is equal to multiplication. It's not normal convolution. Convolution is tricky mathematical operation, but multiplication is multiplication, just like number multiplication. This is function multiplication. So multiplication of reciprocal lattice and Fourier transform of structure vector, not Fourier transform of protein structure, is equal to structure vector. So this one continuous version of this one, or this one is discrete version of this one, vice versa. But we have name for this one structure vector, but we may not have proper name for this one, but continuous version of protein structure. So this is a little bit tricky, but this is the very core concept in crystallography. Also, beyond this, no more secret, no more difficult mathematics. That's all. But once you capture the meaning of this kind transform pair, this one, Fourier transform pair, this one, Fourier transform pair, this one, Fourier transform pair. Mostly through our experiment, we are dealing with this, but we are interested in here. So we should study the other three parts. These are kind of tool for thinking, not actual topic we are looking at. But this is final outcome. This is the sample. This is for experiment. We are covering these three. Rarely, even we do not have name for this, but still continuous function. But it's very like physics-oriented scattering experiment. If we have single molecule like this, if we expose X-ray, we will have image like this, continuous scattering, not discrete scattering like this. So calculating original image based on this one can be very challenging. Also, so better than try to capture or investigate structure starting from this with X-ray. If you have this one, diffraction or scattering pattern will be very much simplified into discrete term. Okay? So we have some spot, not continuous shading like this. So important mathematical or physics. Okay? Without understanding this, reconstruction of electron density can be meaningless. So when we are saying reconstruction, let's go back to here. This is about computational aspect. Once we have this kind of data, we can have equivalent one in real space. But do you know the word GRID? Grid. Grid point and function value over each grid point. Like HKL, also I skipped some background in mathematics, but I talked about discrete one and continuous one. So these are discrete one in terms of function. So we should have discrete one even in real space. So real space equivalent to this kind of discrete function in reciprocal space is electron density grid. Although we are talking about continuous x, y, z, but think about Fourier dog again. Dog, Fourier dog. To be precise, if you have numbers, not images like this. Image is representation. Image or photo like this is not whole data. But if you present this red dot with numbers in RGB, red, green, blue, we may transform mathematically. Then we may have photo like this. Two-dimensional data into two-dimensional data. Different color, different color. Okay? Likewise, cat, Fourier transformed cat. They should be equivalent in terms of data amount, in terms of sampling point. Likewise, here, if you have, let's say, several thousand, we should have several thousand here. But here, several thousand in HKL, but here, several thousand in XYZ. Then we have equivalent sampling in reciprocal space, equivalent sampling in real space. They should be equivalent. Then we can transform vice and versa without losing any kind of information content. If you lose some information content in one side, transforming back to original space can be noisy. That's the topic, what was explained in Fourier dot and etc. And that's the topic here discussed in section 2. Effects of incomplete data on reconstruction, vice versa. Not only electron density, but also structure factor, or they should be equivalent. But in this chapter, we are concerned about reconstruction of electron density to reveal protein structure. So mostly we are concerned about incompleteness in reciprocal space or diffraction space. Those will result in noisy imaging in real space. Okay. So incompleteness has something with equivalent sampling. Unless we have equivalent sampling, we cannot avoid noisy reconstruction. Okay. Any question? Am I too fast? I'm almost done. Map. Unless you have question.
I have.
Yeah.
The grid will be in the real space or the reciprocal space in this case?
You can imagine grids in both space. In reciprocal space, we already have such a grid along HKL points. Likewise, we can imagine same kind of grids in XYZ fractional. But fractional, like HKL, we can have equidistant grid, not a randomly spaced grid. Okay. So using grid, we can have equivalent sampling on each side. Without having equivalent amount of data, we will face incomplete data on one side, and that will result in some errors. But we have two different kinds of missing: randomly missing, or missing some special part, like a strong intensity spot can be lost when we encounter detector dynamic range problem, as you had at Poang synchrotron. His crystal was so well diffracting, so with the just smallest exposure time, 1 second, we had saturation on detector. So we cannot measure strong spot accurately. So in such a case, we may experience missing strong refractions. This cannot be serious problem, but missing strong refractions can be problem. Also, wedges near to some special direction we may miss depending on crystal geometry. So such a missing can result in different imaging problem. Okay. That's a part for incomplete data issue. And as a conclusion, phase problem and phases in electron reconstruction. But what is phase? P-H-A-S-E.
Angle.
Phase can be connected with angle, but phase itself is not an angle. So to be accurate, we are talking about phase angle, like phase problem.
Space.
Phase has something with interference. Even in signal processing in electronics, if you are in phase, we have strong interference or constructive interference. If we are in out phase, they are destructive or noisy, simply canceling. So phase is related with interference. But what is phase problem and what is phasing in crystallography? Now we are done with map, grid, and I'm assuming that we are ready to jump into the word phase. Today, mostly last time we were playing with figures. But not only figures, today we are playing with words. W-O-R-D-S, words. So finishing electron density as a function, also map as a representation, also just mentioning something about equivalent amount of data sampling, we are jumping into the word phase. Okay. This is done now, and we can focus on phase. So to save our time again, let's look at this again. The very figure we encountered even at chapter 1, and this is the very main figure in this chapter 9. Here, this is phase, because 2 pi was taken, so this is not to be honest, this is a phase angle, as Muhammad said. But if you divide pi by 2 pi, this is pi, Greek alphabet pi to denote phase angle. If you divide phase angle by 2 pi, this will be phase. In phase, multiple of integer. Out phase, fractional of integer. If they are not in integral part, if they are in integral part, this exponential part will be number 1. So, or constructive. Otherwise, it will be interfering. So, it will result in destructive interference. So, this is mathematical definition of phase angle in crystallography, also phase in crystallography. But what is the phase problem and phasing in crystallography? I'd like to talk about something in model building. Model. Model building crystallography is two-step process. First one is phasing. Second one is refine. Oh, you're good at refinement or refining. Okay. Refining. What is phasing and what is refining or refinement? Who can explain? To be simple, let's take out ing and let's take verb form. Phase as a verb, refine as a verb. Refine, making good, making better. But phase is not refine. Phase is something else, and as Muhammad correctly reminded, phase is connected with angle in such an equation form. Also, phase is related with interference, as I explained. But what is phase in model building, in crystallography? Model building in crystallography. So I'm asking you, Sanguk and Muhammad, particularly Sanguk, because he has done kind of model building. Model building consists of two parts, phasing and refinement. What you did in phasing?
Phase will determine the primary positions.
Determine. He used the word determine. Determine, yes. Determine. Determine. Determine what?
The primary positions
Primary positions of which?
of the atoms and molecules.
Then all done.
No, and then will be refinement. That will be to improve those positions.
But look at electron density at right side. Are you looking at any kind of atoms there?
Electron density.
No, there are no atoms. But when we will convert it into the model, then we will convert it into the structure of including atoms and molecules. Those positions of atoms and molecules will be determined by
That's the reason why I'd like to take time to share meaning of phase or phasing today. I realized that I gave wrong impression for Muhammad and Sanguk in terms of phasing status. So to be honest, today we started with Fourier dog and dog, Fourier cat and cat. They should be equivalent. Don't forget the word equivalent. Equivalent means we can take one side and depending on computation, we can transform the other side. It doesn't involve any kind of design effort. It's not new creation. Same entity in different representation through computation or through mathematics. That is the point I'd like to emphasize, equivalency between these two functions and these two different spaces. But phase should be understood without involving any kind of position, as Muhammad said. Here, left side, yes, sure, we have protein structure cased in three-dimensional lattice. In the middle, we have diffraction data. At the right, we have electron density contour map drawn in 2 dimensions, but it can be rotated through computer display program, and it can be 3-dimensional representation in single level contour. As I emphasized, it's not in multiple level contouring. But here, particularly for next chapter, chapter 10, we are dealing with experimental phasing. For computational phasing like molecular replacement, we are phasing the structure using 3-dimensional coordinates, so we may have impression that we need position, atomic position for phasing. But phasing itself, like here, like Doug and Fourier dog, this is purely computation. Equivalent one, as long as we have enough data here and enough grid here. this should be purely computational one. So, without knowing any position, once we have FHKL and pi HKL, I would like to say pi HKL, phase angle for structure factor at HKL. FHKL here, magnitude to F. Okay? So once we have F and pi together, then with the help of this equation, we just need to plug numbers here. Simply, this denotes FHKL. H stands for HKL triplet. Here, pi HKL. Okay? Then we can plug numbers there, and here H dot R means HX plus KY plus LZ. H multiplied with X plus K multiplied with Y plus L multiplied with Z. That's all. So once we have data on each HKL, F data and phase angle data, we can plug numbers for computer. Then we should have electron density on grid, because these are for HKL. It shouldn't be minus infinite plus infinite, as I mentioned in previous lecture per semester. This should have some limitation on maximum minus H, minimum maximum H, minimum H. Okay. Then we have grid, electron density grid like this, or electron density quantum map like this. So I'd like to emphasize, once we have phase itself, we can reconstruct electron density map. Okay? So once we determine phase, we can determine overall structure like this. So phase gives overall structure. I'd like to correct some impression, because through molecular replacement, both of you are relying on molecular replacement, so phase can be connected with position for that case. But phase in general gives us overall structure. Refinement kind of detailed structure. Okay. So the reason why Fourier transform is good for imaging in general signal processing is Fourier transformed data are immune to noisy data. So to be immune from noisy situation, we transform the data and we are sending transformed data to other place. Then we are reconstructing such a data into original coordinate. Then even though we are susceptible to noisy transmission environment, we can conserve original information which are very relevant to us. So I will erase this. Anyway, take this word, phase and refine. You should connect this main word. Phase for overall structure, refine for detailed structure. So two-step. Then I will explain why two-step process is good for us from the perspective of signal processing or signal delivery. Okay? Also, I'll open up this one.
Can I go to the restroom?
Ah, yes, yes. I'm sorry. Can we have some break in 5-minute break?
And it will be very beneficial in the future also.
Ah,
We can
you are enjoying such a benefit,
Yes.
although you are not a regular participating student.
I am not regular in this coursework, but
But
I
you
am
already
more
have done
regular
this.
in
Yes.
yes, sir.
You're more than regular. Any officially?
More closer to my subject.
That's correct.
Yes.
Yeah.
Yes.
Also, you are expecting to have structured determination soon. So, you are very motivated because of your own research problem. Now I got your point. He has done, but you should do. So you are the most motivated one.
The coursework is more related to my work and his work, not these two people's work.
But as I explained at the beginning of today's coursework, intellectually, I'd like to write a book on crystallography as a model scientific teaching, because the very point I'd like to explain, but I couldn't find such a tutorial yet, but convolution theorem and incomplete issue of, let me restart again. Here, this book, particularly this chapter, can be very boring from biology student like you, but this is very link between engineer and scientist. Engineer is not only concerned with science, but kind of practicality or realization or reconstruction of reality or representation. I have many words for that, but signal processing in electrical engineering is very core concept. Even smartphone, my phone is LTE, very fast in terms of data transfer. Time to time, it record over 10 megabyte per second, not megabit per second. It's better than our official network. Official network for internet, ours is 100 megabit per second. That corresponds to around 10 megabyte per second, but rarely it reached such a high speed. But mine, LTE, it's a wired one, but this is wireless one. How can we receive such a data, huge data, if you count numbers like that? Each character, 100, just 10 megabyte means 10 million characters per second. Even your PDF file, less than 10 megabyte usually. So images and characters, even simple encyclopedia without figures can be transferred within a second. Okay? Huge data can be transferred in such a short time. How can it be possible? We have very noisy environment. I'm talking about electrical noise, electromagnetic noise. We have signal not only for LTE telecommunication, but also even solar radiation, solar electromagnetic radiation, and even surrounding lab facility, we have many electrical noise over space. Practically, it's a kind of miracle for me. Even if you may not appreciate such a miracle, I'm talking about technical miracle. Just before 15 years ago, when I was graduate student, almost 20 years now, not 15. It was 1995. That's the time I really had internet connection at my lab. At that time, it was less than 1 megabps, 10 kilobytes per second. Now, at my home, I have 1 gigabit per second internet connection, higher than our institutional one. It's amazing in terms of data transfer speed. Formerly, even downloading single JPG file, I'm talking about image file over internet, it took long time, so reading some web pages containing many JPG images can be too time consuming. It took very long time. So we had two versions, without image and with image. For high-speed internet, we have image version. For low-speed internet, especially from home was slow at that time. Even home, we didn't have any internet connection. We just had telephone modem for such a connection. Do you know such a modem?
Yeah.
But nowadays, we are living in totally different in terms of data transfer speed. How such a thing can be possible with noisy environment like this? Even this time worse, because we have many signal source. Formerly we had rarely such a source, but we have many access points, many telecommunication companies, but even under the circumstance, we have more noise decision, we have higher transfer speed. That is possible because we have technique or technology to overcome such a data transfer through noise environment. That is key concept in signal processing, and that is the same concept in crystallography actually. Actually, what we have here in complete data, so I direct emphasize this point. Randomly missing refractions as a result, I told you, it's not a problem at all. But if you miss some part systematically, strong refractions are lost. Then we have some effect, kind of rippling effect. Also, if you miss whole part in reciprocal space, then that could be problem in real space. But if you miss randomly in reciprocal space, that will not have any effect, practically, any effect on real space. So we are fine. You may find some explanatory figures here. This is something with signal processing or signal transfer over space over time under noisy conditions. Here, we have data and function in real space. Also, we have corresponding data in other space. In signal processing, we are converting, for example, our own voice. Now, voice is not transferred as a sound. It was digitized, and it was transferred as a digital data. Okay. Also, it was digitized not only in terms of voice amount, but it was transferred in frequency level, not data in time domain. Data in time domain can be transferred into data in frequency domain. So even if we have noisy data, it's not actually data. Data, we can distinguish this. data as we measure actually two parts. Data is actually signal plus noise. As what is the singular form of data? Because data is plural.
Data.
Oh, correct. Thank you so much. Datum is a singular form of data. Data is plural. So signals, we are talking about signals and noises. Okay? On sampling point, like grid. Data on sampling point. So here, real space, reciprocal space. You can make this kind of analogy. Data in time domain, data in frequency domain. Time and frequency are reciprocal to each other. Like real space, reciprocal space are reciprocal to each other. Okay? Once we have signal in time domain, we have signal in time domain. Then, if we convert such a signal into frequency domain, okay, then in frequency domain, we can convert or we can transform data into time domain again. Okay, vice versa. Time domain, frequency domain can be equivalent in terms of information content. So they can be switched to each other, like dog and Freya cat and cat. Okay? But in time domain, we are very vulnerable to noise. So we should transfer signal into frequency domain when we can avoid such a noise. Once we convert into frequency domain, we can do frequency filter. Very high frequency and very low frequency, although we have such a interference or noisy, additional noise in frequency domain transfer, they cannot be real. So we can filter it out. By filtering out such a high and low, we can reconstruct only valid frequency range. Then our time domain signal as a voice, our own voice as an information, can be clearly heard at the receiver. Okay? Likewise, even if we have some problem here at reciprocal space, like frequency domain, missing data randomly cannot be serious problem at all, because that is like a noisy interference in frequency domain for voice over time. If we back transform, Fourier transform again, voice can be very clear. But we have some rippling problem or some artifact through such a transformation. But basically, although we are losing some point randomly, that should not be a problem. Also, we have some errors at the magnitude of each, no serious problem. If you're losing most of them, that should be a problem. But as long as we have enough amount here, these data will be very reluctant to noisy interference. That is the power of Fourier transform in signal processing and Fourier transform in crystallography. So our structure determination is very robust based on this kind of mathematical power or computational power to suppress noise. We are suppressing noise in frequency domain. We are just removing some high frequency, low frequency noise just filtering. Likewise, we can suppress such a noise in reciprocal space. So transform signal in frequency domain to signal in time domain, just Fourier transform. Likewise, signal in reciprocal space into signal in real space, just Fourier transform. Once we have phase. But to determine phase in crystallography, we need either experimental phasing or computational phasing based on molecular replacement. So phasing is key concept of imaging in crystallography. Phasing itself, once we know the phase, actually phase determine overall structure, which is very reluctant or robust to noisy interference. Okay. Once you know this concept, you can be very multidisciplinary and you can understand the engineer's mind. As a scientist, we are trained not, most times we focused on signal in experiment, but we are not well trained to deal with noise. But in reality, always we have noise. Engineers are very concerned about noise. Electric engineers are very hardware, any kind of hardware. Even we have some certificate in compliance as a certificate for such a company. I forgot the name, but anyway, this is key concept in crystallography and engineering. So it's better to capture this, and this chapter should be the link between science and engineer. Although it was not very well explained in the textbook, by having this kind of core concept, anyway, I emphasize this again. Frequency like reciprocal lattice, and time domain like a real space domain, space and time. Actually, they are in the same kinds. Frequency and reciprocal space. Okay. You can memorize this core. We do not have very many concepts. We just have this concept. Okay. This is power of crystallography, and that's why we are not too much concerned about missing data. We are not too much concerned about wrong or miscollected data, as long as they are not majority. Okay. Question or suggestion? And from next week, I got some recommendation from Sang-wook. It's better to have kids in between, to have break, and we can enjoy such a break. Having 2 hours coursework straightly can be very demanding for both of us. So taking quiz at the beginning or finishing quiz in the middle can be nice. Okay. Question or suggestion, or your discovery or enlightenment you had.
Go to another slide that is about the missing data.
Go through your own pages you would write. That's an old one, and detailed chapter contents.
No. The missing data.
Missing data, that's the book chapter content. I didn't show detailed figure. I just explained missing data in terms of this.
Okay, yeah, this.
Here, effects of incomplete data or missing data. First effect, randomly missing refractions, no effect. Okay, it's okay, simply it's okay. That's the reason why we can have R working value and R free value. Actually, we are omitting 5% or 10% of data in diffraction to evaluate whether refinement is going well or not. So, randomly missing, no problem. Okay. Secondly, strong intensity data missed due to some reason. Some reason is like this: overflowing intensity for very strongly diffracting crystals. Then we have problem not to have correct structure in low resolution structure, kind of rippling effect. But in terms of higher resolution, it's less detrimental. Data wedges, special area from reciprocal spaces, can distort real space. And lattice disorder and anisotropy, kind of special topic, so I didn't talk about anything regarding this.
If we miss in the randomly missing reflections, if we miss some important data in that.
That is tricky part. Nothing special in reciprocal space as long as we are missing randomly. That is power of reconstruction. If we miss something in one space, that means we are losing something in that space. That is total loss at that particular region in that space. We cannot recover it. But once transformed, we are not losing data in original space. We are not losing data in electron density. We are losing data in reciprocal space. So, losing data in reciprocal space is not losing data in real space. That is a secret. That is the point I use the word equivalent. I didn't say same. I didn't say same amount. I didn't say equivalent amount. That is a little bit tricky to explain full meaning, but through this coursework, I'd like to share that meaning. It's not easy to comprehend such a meaning, but this has something with transformation. Once transformed, also it has something with the nature of Fourier transform. Fourier transform by itself is dealing with periodicity. The reason why we are using Fourier transform to represent structure factor, also to be useful with electron density reconstruction, is like this. If we lose some component in reciprocal space, it will not affect major component or major form in real space. It's not directly linked. It's okay to lose something there. Still, we have enough amount to have majority in the other space. So it was very good reminder for all of us. Effect of losing data in reciprocal space will not affect very much in real space. That is the very reason why we can do crystallography. crystallography itself is not direct imaging, but we can enjoy its indirect nature, because by being indirect, we can overcome noise problem. Here, even we didn't start something about space problem, but next time, anyway, we have enough time for this chapter. So next time, next week, we will talk about phase problem in details. But not only phase problem, we should emphasize noise problem. So this part has something with noise or incompleteness. That is fine as long as we are losing something in reciprocal space. We still have something in real space. That is my message for you, and for your own intellectual challenge, read this textbook, this particular chapter under that regard. Especially read Fourier duck and duck, cat and Fourier cat. Then they will explain something for you in terms of missing data effect. Okay? For others, it may be a little bit boring, so I'd like to stop here, and I will come back phase problem again, okay, with the help of distinguishing phase and refinement. Okay. But Muhammad, you did make very good point for all of us. Losing some data in one space is not equivalent to losing data in other space. Okay? We do not have same impact. Basically, we are very robust in terms of losing data in reciprocal space. 상욱 씨한테도 좀 도움이 됐나요? 그 개념이? 어쨌든 구조를 풀었으니까 문제는 아닌데. So, see you next week. Okay. I'll prepare some quiz to test whether you understand this concept or not.